So the different types of threads we will see now. One is called as the user level threads and the other one is the kernel level threads. Now let's see the user level threads. User level threads do not have kernel or operating system support. So uh, it doesn't have any support of operating system and they exist solely in the running process. So it is just part of the running process. Even if a process contains multiple user threads, so now assume there is a process which has got multiple user threads, the OS treats it as a single thread only. Suppose you have process 1 and you have 3 threads, thread 1, thread 2, thread 3. But all of them, they are treated as a single thread. The operating system treats it as a single thread because it is a user level thread. And it will not switch the execution among the different threads of it. Means you have a user level thread, that is you have a process, and the process you have 3 threads, thread 1, thread 2, thread 3, and all of them are user level threads. So even the process is a user process, and the threads are also user level threads. So you have thread 1, thread 2, thread 3. Now the operating system treats it as a single thread. So all the 3 are treated as only one thread and it will not switch the execution among the different threads of it. So what do you mean by that? Suppose thread 1 is going to a waiting state. It requires some IO. Then in the normal case, it has to get switched to the other thread, thread 2. But in this case, it will not switch. If thread 1 is waiting for some IO till it finishes, it will not proceed with thread 2. So there is no switching. The operating system will not switch among the different threads of it. Now, it is a responsibility of the process to schedule each thread. Now, in case of user level thread, the process should do the scheduling of each thread as and when required. So operating system will have no role here. The operating system will treat all the threads as one thread and it will not perform any context switch between threads. So whatever it has to do, that has to be done by the process itself because it is a user level thread. In summary, user level threads of a process are non-preemptive at the thread level from operating system perspective. Means for operating system, if it is a user level thread, it will not do preemption. Means it will not do context switch from one thread to another thread. The operating system will never do the context switch. That is nothing but preemption. So whenever it is executing at user level thread, then it is solely responsible of the processes to take care. Operating system will treat all the threads as just one thread. So internal context switch or preemption will not be done by the operating system. So this is about the user level thread. Now going to kernel level thread or system level thread. So kernel level threads are individual units of execution which the operating treats as separate threads. So kernel level threads are treated totally separately. The operating system interrupts the execution of the currently running kernel thread and switches the execution to another kernel thread based on scheduling policies implemented by the OS. Unlike user level thread, in case of kernel level thread, they are treated separately. Example, you have a process and you have 3 kernel level thread, thread 1, thread 2, thread 3. Then the OS interrupts the execution of the currently running kernel thread and switches the execution to another kernel. Suppose thread 1 and thread, you have 3 threads. Thread 1 wants some IO operation, then the operating system only will interfere. It will switch the execution to another kernel thread. So based on the scheduling policies implemented by the OS. So this is a major difference between the user level and the kernel level thread. Now let's go to the next point. Now, the execution switching of user level threads happen only when the currently executing user level thread is voluntarily blocked. Now I'm talking about user level threads. So you know user level thread, operating system will not interfere. Now I want to perform a context switch. You have 3 threads, thread 1, thread 2, thread 3. Now we want to perform a context switch from thread 1 to thread 2. It can happen only when thread 1 will voluntarily block itself. Only if the thread 1 voluntarily blocks itself, then it is the context which will go to the next thread. So hence no OS intervention and system calls are involved in the context switching of user level thread. So I'm repeating, in case of user level thread, you know very well OS will not interfere for context switching, that is switching from thread 1 to thread 2, but still we have to switch from thread 1 to thread 2, means then thread 1 should voluntarily block itself, then automatically the control will go to thread 2. But in that also the OS will not interfere, they are not involved in that context switching of user level thread. So henceforth, since OS does not interfere and only the user level thread only will resolve itself by blocking, by voluntarily blocking itself and giving the control to the next thread. Because of this, the entire process of context switching in user level threads are very fast. They are very fast. Now let's go to the next point. Kernel level threads involve lot of kernel overheads. As you know that the operating system are involved in that. However, kernel threads maintain a clear layer of abstraction and allow threads to use system calls independently. So here in case of kernel level threads, it involves lot of kernel overhead, and there will be a context switching. Henceforth, another advantage is kernel thread maintains a clear abstraction and it allows the threads to use the system call separately. Individually, it can use it because they are treated it separately. So these are the points of kernel level threads. So now let's go to the thread binding models. There are 3 models, and now we will see to which category of thread we are using. Now let's see. Many to one model means many user level threads are mapped to a single kernel threads. So you are trying to do binding. If at all the user level thread wants to map to the kernel level thread in many to one model, in this model, many user level threads are mapped to a single kernel thread, and the kernel treats all user level threads as single thread only, and the execution switching among the user level threads happen when a currently executing user level thread voluntarily blocks itself. This we have already seen. So in case of many to one model, many user level threads are mapped to a single kernel thread, and this particular kernel treats all the threads as one. So the context switching happens only if the user level thread voluntarily blocks itself and releases CPU. Then only it will go to the next thread. So the best examples are Solaris green threads and GNU portable threads. Now coming to one-to-one model, each user level thread is bonded to a system level thread, to one kernel or system level thread. The best example for this is Windows XP, Windows 2000 and Linux threads. They are all examples of one-to-one thread models. Now coming to many, in this model, many user level threads are allowed to be mapped to many kernel threads. So you have ABC as user level thread, XYZ as kernel level thread. So A can be mapped to XYZ, B can be mapped to XYZ, C can be mapped to XYZ. So many user level threads can be mapped to many kernel level threads. So the best examples are Windows 2000 with thread fiber package. It is not just Windows 2000, along with that you have a thread fiber package. So this combination will support many to many models. Okay, so now let's differentiate between thread versus process. Quite important. Let us differentiate both thread and process. What is thread? A thread is a single unit of execution and it is part of a process. All of you know, it is a part of process. Whereas process is a program and execution and contain one or more thread. This you agree. Let's go to the next point. A thread does not have its own data memory and heap memory. This we saw, it does not have its own memory. It shares the data memory and heap memory with other threads of the same process. So for process, all the memory will be given. So thread inside that process will share data and heap memory. Whereas coming to the processes, each process will have its own code memory, data memory, and stack memory. Now let's go to the next point. A thread cannot live independently. It lives within the process. We know that thread is a subset of process. In here, a process contains at least one thread. So usually it contains minimum one thread. Now, there can be multiple threads in a process. The first thread calls the main function and occupies the start of the stack memory of the process. So usually there are several threads, but the first thread will always occupy the start of the stack memory. Now coming to this, threads within a process share the code, data, and heap memory. Each thread holds separate memory area for stack. So each thread, we know that for each thread a separate stack is allocated. Now coming to the next point, threads are very inexpensive to create, whereas processes are very expensive to create because it involves many OS overhead. Now, coming to thread, context switching is inexpensive and fast. It's fast, whereas here, context switching is complicated and involves a lot of operating system overhead and is comparatively slower. Now, if a thread expires, its stack is reclaimed by the process. If the thread dies, then all its resources, the stack, will be reclaimed by process. But if the process dies, then all the resources will be reclaimed by the operating system. So when once the process dies, all the associated threads of the process also dies. So these are some of the differences between the threads and the process.